Good evening. We are going into our fifth chapter, which is laws of motion. We start this chapter with the first topic, that is Newton's first law of motion, which is also called the law of inertia. This word inertia means resistance to change. So if a body is at rest, it continues to stay in rest, and if it is already moving, it continues to move in uniform motion if the net external force acting on it is zero. This property of a body is what you call as inertia, and this law was put forward by Galileo. Now, Sir Isaac Newton built on Galileo's ideas and laid the foundation for mechanics in terms of three laws, that is Newton's three laws of motion. And what we are now going to first discuss is Newton's first law of motion. In Newton's first law of motion states that a body continues in its state of rest or in its state of uniform motion unless and until it is acted upon by an external force. So, it means that if the net external force acting on a body is zero, then its acceleration is zero. That is, if there may be many number of forces acting on a body, but if the net external force happens to be equal to zero, then the body will have no acceleration. That means if it is at rest, it will continue to be at rest, no acceleration. If it is moving with a particular velocity, it will continue to move with the same velocity without changing its velocity because its acceleration is zero. So that is Newton's first law of motion, and we now go into Newton's second law of motion. Newton's second law studies the motion of a body. So, in order to study the effect of force on the motion of a body, we first need to consider the factors that affect force or factors that affect the force acting on a body. Let us first look at this factor mass. Now, suppose we have a car and a heavily loaded truck. So, obviously, this heavily loaded truck has much higher mass than this car. Now, let's say both of them are at rest and you are now applying a force to push them and put it into motion with the same speed. So, obviously, this heavily loaded truck with a much larger mass will require higher force or larger force to put it into motion, and so that both of them acquire the same speed. So, greater the mass, greater the force required. Another factor that will determine the effect of force is, as you know, speed. Let us consider the example of, let's say there are two cyclists, which let's say both of them have the same mass, but one cyclist is going at a really high speed and the other cyclist is at a lower speed. To bring these two to rest, you have to apply a force, and the force that has to be applied on this cyclist who is moving with a larger speed definitely has to be higher. So the other factor that determines the effect of a force is the speed. So the product of these two factors, that is mass into velocity, is what we call as the momentum of a body. So the product of mass and velocity of a body is what you call as the momentum of a body. Since velocity is a vector, this momentum is also a vector. This momentum has its SI unit as, this is kilogram, and velocity is meter per second. And in the first chapter, when we discussed the dimensional formula, we know that the dimensional formula of this momentum is m, and for velocity it is Lt raised to minus 1. So this momentum is a vector quantity. So this momentum, the rate of change of the change in momentum or mass into V is an important factor that determines the effect of force. There is another factor that determines the effect of force. Like, let's imagine you are playing cricket. So, as the ball comes towards you, it comes with a certain momentum. It has a mass and it has a velocity. So, it's coming towards you with a particular momentum, mass into velocity. Okay. Now, to bring it to a stop, its momentum has to change to zero because the velocity has to come to zero. So, when you catch the ball, it reaches your hand with a momentum mv, and then it has to reduce to zero when you stop the ball. Now, the time interval in which this takes place, let's call it as delta t, is an important factor that determines the force exerted on you by that ball, because you will notice that when you take the catch, you will move your hand backward. If you do not do that, and if you suddenly take the catch, if the time interval is very short, then what happens is this change in momentum takes place in a very short interval of time. The force exerted on you will be higher, you will experience more pain. The effect is much larger. Instead, if you take the catch by moving your hand backward, you are bringing this change in momentum at a greater time interval, which means the effect of the force is lesser. You will be hurt lesser. I mean, the pain you feel will be much lesser. So, this time interval in which this change in momentum takes place is another important factor that determines the effect of the force. So, we may write the two things. That is, we may write that this force is directly proportional to the change in momentum, that is the mass into velocity. Greater the mass, greater the force, greater the velocity, greater the force, divided by delta t. That is, if this change in momentum happens at a shorter time interval, the force exerted is larger, but if the time interval in which the change in momentum happens is larger, that is by moving your hand back, you will see that the force is lesser. So this is Newton's second law, which says that the rate of change in momentum of a body is directly proportional to the force applied, and it takes place in the direction of the applied force. Now, if we are talking about an infinitely small time interval, we may write this as F proportional to dp by dt, because we are talking about infinitely small time interval. Or we may write F is equal to a proportionality constant k into dp by dt, and for simplicity we may take this k to be equal to 1, which means F is equal to d by dt of momentum is mass into velocity. Now here, mass, for cases where we take mass to be a constant, I may write F is equal to mass into dv by dt. Mass I took outside, dv by dt. Rate of change of velocity we know is acceleration. So we may write F is equal to ma, which is Newton's, it's a consequence of Newton's second law. Newton's second law simply states that the rate of change of momentum is directly proportional to the applied force, and this change in momentum takes place in the direction of the applied force. Now, as we discuss this F equal to ma, Newton's second law, we need to think about 4 points. The first thing is, if this F is equal to 0, then we know acceleration is 0, right? So, the first point that we will discuss here is, if this F is equal to 0, then it implies that acceleration is 0 from this formula. So, this is consistent with Newton's first law, where we said that if the net external force acting on a body is 0, the body will have no acceleration. It will continue in its state of rest, or it will continue in its state of uniform motion. So, Newton's second law is consistent with Newton's first law. The second thing that you need to keep in mind is this F equal to ma. Now, we were discussing about a particle. It is actually applicable to a system of particles, like for example a rigid body like this, which may contain n particles. Now, in this rigid body, which it's a system of particles, if the net external force acting on this rigid body of n particles is 0, then the acceleration of the system as a whole will be 0. Now, the third thing that you need to remember is this Newton's second law is a vector law, which means force, a vector, is mass into acceleration is the other vector. So, you may write Fx is equal to mass into Ax, and Fy is equal to mass into Ay, and Fz should be equal to m into Az. Let me explain what you mean by this. See, suppose we have a body like this, okay, and you apply a force F. We can resolve, if this is acting, if it is in a plane, you can resolve this force into two components. One, the Fx, if this is theta, this will be, as you know, F cos theta, the horizontal component, and this is going to be Fy, which is a vertical component, F sin theta. If this force is applied in space, it will have a third component, that is Fz. So now these two components, we have Fx and Fy. Now as this body moves, it will have an acceleration along the x-axis and an acceleration along the y-axis. What is to be noted is, this component of force Fx can have an effect only in the acceleration along the horizontal. That is, this Fx can affect only this Ax, acceleration of the particle along the horizontal direction. Similarly, Fy can have an effect only on the acceleration of the particle in the y direction. Or Fy cannot change the velocity of the particle in the horizontal direction. Fx can have no effect on the velocity of the particle in the y direction, which is what we discussed in projectile motion, if you remember. In projectile motion, what we discussed was that suppose we project a body with an initial velocity u. Okay, so once you project this body, let's say we projected the body with an initial velocity u, so that this component is u sin theta, this is u cos theta, and it has a component here u sin theta. Now once it is projected, it is under the action of the gravitational force, and that gravitational force is acting only in the downward direction, which is Fy. So what happens here is, this component of velocity along the horizontal direction, the acceleration is 0 simply because Fx is 0. So this u cos theta, throughout its flight, u cos theta at all points will remain the same. No change, because no acceleration in the horizontal direction, since the component of force along the x-axis is 0. Gravitational force is only along the y-axis. Whereas this component u sin theta continuously changes. Because of this component Fy, u sin theta will start from here at the maximum point here. This u sin theta, the vertical component uy, will reduce to 0. And then as it moves down at this point, it will reach back to u sin theta. So that is what I meant when I said this second law, Newton's second law, is a vector law, and you may write Fx is max, Fy is may, and Fz is maz. And then the last point is that this Newton's second law is a local relation, which means the acceleration of a particle at a particular instant depends only on the force on that particle at that instant only, not on some previous force that may have acted upon the body. For example, suppose you're traveling in a train and you throw a stone. So while the stone was in the train, it was being accelerated because of the force exerted on the train. But once it is thrown, it is only acted upon by the gravitational force. So as it is falling, the only acceleration it can have is the acceleration due to gravity. It cannot have any, its acceleration cannot depend on any force that may have been applied on it some time before or some previous history of force. The acceleration of a particle at any instant depends only on the force acting on the body at that instant. So these are the 4 points that you must keep in mind when you discuss Newton's second law. And the last is Newton's third law. Every action has an equal and opposite reaction. So beautifully phrased that it has become part of common language. Every action has an equal and opposite reaction. So which means if we have two bodies, let's say we have a body A and we have a body B. If A exerts a force on B, let's call that as force exerted by A on B, then B will exert a force on A, which is FBA, force exerted by B on A, such that FAB is equal to minus FBA, which means the two will be equal in magnitude but opposite in direction. Now the thing is, in that case, if we have a massive earth, and if you throw a stone up, you know that the stone will fall down towards the earth, Because the earth exerts a gravitational force on the stone. If the earth exerts a force on the stone, so naturally the stone must exert a force on the earth and the earth must move towards the stone. But that doesn't happen simply because the earth is so massive that this force becomes, the effect of the force becomes very negligible. So since the size, the mass of the earth is very high, the force is there. The stone is exerting a force on the earth, but its effect is negligible because of the large size of the earth. Now, again, when you discuss Newton's third law, you need to keep three things in mind. One, this is called the action and this is the reaction. So, which means that both action and reaction are essentially force. You may call this as a reaction and this as the action, not a problem. But remember, action and reaction are both forces. They are equal in magnitude but opposite in direction. The second thing that you must remember or keep in mind is you would tend to think that action is something and the action happens first and after that the reaction happens. It's not true. Action and reaction are happening at the same instant. For example, suppose I'm standing on the ground. I don't sink in because my weight, that is the action, acts in the downward direction on the floor. But the floor gives me a reaction in the upward direction which is equal to my weight. So because of that, I stay on the ground without moving down. So let's say I'm standing on the ground. This is the floor. And as I stand on the floor, my weight is acting in the downward direction. Let me call that as action. The floor exerts an equal but opposite reaction, and since the action and reaction are equal in magnitude, you don't sink down. But action and reaction are acting at the same instant. So this is important because if somebody slaps you and you get angry and slap him back, that is not action and reaction. Action is the person slapping you is the action. At that same instant, your cheek is exerting a force on his hand, and that will be the action-reaction pair in that case. The third thing to be kept in mind is action and reaction happen on two different bodies. That is, action here is happening on B. That is, force exerted by A on B. So, action is happening on B, but reaction is happening on A. So, action and reaction are two pairs of forces happening at the same instant but acting at two different bodies. Because of which, you cannot say that the net force here is zero because they don't act on the same body. If on the same body I have two forces acting in opposite direction and they have equal magnitudes, then the net external force on this body is zero. But in our case here, as I hit this with a pen, the action is on the duster and the reaction is on the pen. So you cannot say that the net external force on the duster is zero. So these are the things that we need to discuss in the first three topics, that is Newton's first law, Newton's second law and Newton's third law. Thank you and good night.